At the most basic level, there are two ways to return a first serve. A player can return the ball with topspin or chip the ball back into play with backspin. Between these two options, the topspin return is favoured. In our sample of 1,451 first serve returns observed in 20 matches of the 2021 Brest Challenger tournament, 72% of first serves are returned with topspin, and only 28% are returned as a chip, and even fewer, as we will see, are chipped back by choice. However, some highly successful players consistently use the chip return as a tool to either neutralize the rally with a deep floating chip or draw the server into the court with a shallow, low bouncing chip. The primary goal of this analysis is to understand the effectiveness of the chip return versus the topspin return, as measured by the expected probability to win the point. If you would like the results right away, check out the short version of this video. Here, we build up towards the results first and outline them at the end. At first glance, it doesn't look good for the chip return. On average, in our sample, the returner wins around 40% of points whenever he returns with topspin, versus only around 20% of points when he chips the ball back. However, this view is slightly unfair toward the chip return. To understand why, carefully consider these 8 returns and what they have in common. All these returns have 3 things in common. They're played off the backhand on the stretch as a chip. In fact, there is virtually no way to return these with topspin. On these serves, the returner has no choice. He's forced to chip the ball back in. For the lack of choice, there is nothing to discuss. The serve is almost an ace. You do what you can, chip it back in, and pray for the best. What can be discussed are returns where the topspin and the chip are available. To distinguish these cases from forced chips, we employ a technique called propensity score matching, or PSM for short. Our PSM model looks at the speed of the serve, the height of the bounce, how deep the returner is positioned, whether the serve is to the backhand or forehand, and how far the returner has to stretch to get to the ball. From this data, PSM predicts the probability of the ball being chipped back by the returner, as opposed to being returned with topspin. The arrows here indicate how each factor influences the predicted probability to chip. For example, a chip return is likelier if the serve is faster, or if the returner has to stretch to reach the serve. So how does this propensity model help us differentiate between chips that are forced and chips that are done by choice? If PSM predicts a high propensity to chip, then it effectively believes that there was no way that specific serve could have been returned with topspin. It is a forced chip return. On the other hand, let's say we observe a chip in a situation where the propensity of playing a chip is low. That is, where we would usually see a topspin return. In this case, the chip return is the returner's strong choice. He could have played topspin, but he went for the chip. To illuminate this, consider the 8 lowest propensity chip returns. On these returns, it does indeed seem that the returning player chose to chip the ball back, where he could very well have played a topspin return. We can now use these propensities to focus on chip returns where the returner actually had a choice, and thereby assess the quality of this choice. As we saw earlier, the proportion of points won by the returner on a chip return is just under 20%. If we concentrate on choice chips, we expect that proportion to increase, since we discount those serves that are returned on the stretch under great difficulty. Indeed, we see a modest increase to 23.3%. Unfortunately, even after adjusting for choice chips, we have not yet arrived at a true unbiased picture of return win probabilities. Why? Well, in a perfect world, we'd ask each player to hit 100 serves to each other player in our sample. This way, we'd observe equally many serves and returns for each player. However, our data is generated not by experiment, but in the course of actual tennis matches. In a tennis match, the amount of returns observed by a player is systematically biased. What happens is that we observe more returns from the better player. To illuminate why, imagine player A has a great serve and an average return. Player B has an average return and serve. We expect player A to hold faster due to his strong serve and therefore play relatively fewer points on serve and relatively more on return. Similarly, if A had a great return and an average serve, we'd expect him to hang in for longer in return games, thus playing relatively more points on return again. Yet another way to show this is to look at what happens to win percentage if rallies go on for long. When a point goes on for a long time, the impact of the serve and return is nullified. If both players were equally matched, we'd expect the win probability on long points to be at 50%. So let's take a look at the returner's win probability given the length of rallies. We observe that the return player has a greater win probability in long rallies, indicating that the better player indeed plays more returns in a match, simply due to the nature of tennis scoring. To remove this bias and approximate the experimental setting, we introduce a balancing factor that gives more weight to returns made by the player for whom we observe fewer returns overall. Ostensibly, this is the weaker player. The balance adjustment does not greatly impact either win percentage beyond a slight reduction. A reduction is to be expected since we're counteracting the impact of the better player being on return more often solely by virtue of the data generating process. Our third and final adjustment is connected to something we have just mentioned. The longer a rally goes on, the less the serve and the return matter to the outcome of the point. Therefore, the longer a rally goes on, the less we ought to attribute whether a point has been won or lost to the quality of the serve and the return. This is exactly what we do with our attribution adjustment. If the point is over fast, the return is credited for winning or losing the point to a greater extent. If the point ends only after a long rally, the return is only credited with neutralizing the serve. After the attribution adjustment, chip returns gain around 4% in win probability, whereas the topspin return success rate is slightly reduced. Why there is an increase for chips and none for topspin returns is a combination of many factors, the most intuitively accessible of which is as follows. For the aggressively minded tennis player, there are a variety of ways to end the point on the third shot, either by serve and volley or by baseline winner. These points can be subsumed under the term serve plus 1. On a chip return, the server's probability to win the point on a serve plus 1 is 63%. On aggregate, the server's patience would pay off. If he were to play a setup shot instead of an immediate winner, let the returner scramble, and attempt a winner on the fifth shot of the rally, his success rate would rise to 82%. On a chip return, a serve plus 2 is more successful, on average, than a serve plus 1. The bad news for the server is that the more promising serve plus 2 happens only about half as often as the serve plus 1. The typical server is in a way slightly too impatient on chip returns. Since the attribution adjustment correctly values the return's impact on the outcome of short rallies higher than on long rallies, the server's impatience is reflected in an increase in the success rate of the chip return after the attribution adjustment. After all adjustments are made, chip returns are still 12% worse than topspin returns in terms of winning percentage. The question then is, how good must the chip return be to overcome those 12%? Where should it be placed and how should it be played? Is it better to play a high arcing chip or a low bouncing chip? In the following, we will attempt to answer these questions. We build up our understanding of a good chip by looking at some characteristics of topspin and chip returns in general. First up, placement. As in the case of this example return, we collect the bounce position of all returns in our sample. We then flip returns hit back to lefty servers so that the server's forehand side is always at deuce. This way, we can check whether returns are hit to the backhand side preferentially. We mark topspin returns in orange and chip returns in blue. Now, consider the empirical distribution of topspin returns. Topspin returns are symmetrically clustered around the center of the court, with a moderate preference for the server's backhand. Around 60% of balls are hit to the backhand side of the court. On the other hand, for choice chip returns, we see a more irregular heat map. Some land shallow, others deeper. As with topspin returns, chip returns are hit predominantly to the backhand side. Again, the split is around 60-40. Let us now look at a different facet of return characteristics, launch angle. The example return that we saw just now is chipped back at an angle of 11.9 degrees. Let's see how launch angles are distributed for choice chip returns in general. Within choice chips, we observe two modes at two different launch angles. It does seem to be the case empirically that when a player opts for a chip return, he really opts for either a high arcing chip or, most commonly, for a low, shallow bouncing chip. On the other hand, for a topspin return, the distribution is more uniform. We observe only a single mode. To put numbers to it, the typical topspin return is launched at an angle of 7.5 degrees, the low angle choice chip return at 11.9 degrees, and the high angle choice chip return at 18.1 degrees. Our example chip return left the racket at 11.9 degrees, making it a very good representative of the low angle mode. Let's watch it again in this slide. We now compare the low chip to a representative of the high angle chip returns in the lower right. Both returns are hit at almost the same speed, spin, and height. We therefore isolate the effect of launch angle on ball flight, which differs as follows. The high arcing chip bounces 70 centimeters higher than the low chip, which makes it easier to attack if it lacks sufficient depth. On the other hand, the high chip loses more of its speed. It is up to the server to inject pace. The arcing chip also gives the returner more time to recuperate, which may be especially useful if the serve is hit out wide and carries the returner off the court. With respect to this latter point, let's visualize the impact of a ball's time in flight on the receiving player's ability to reposition on the court. First, consider the original example in the top left. The expanding range of motion depicted here represents the court positions that the returner can comfortably reach, assuming a third of a second of recovery time and a maximum shuffle speed of 4.2 meters per second, which is estimated from our data. The low-angle chip shot gives the returner enough time to recover to the optimal spot, marked with a red X. Had he played a high-angle return, the additional 0.24 seconds of time until bounce would have given him more range of motion, which, in this case, would not have been necessary to reach the optimal point. A comparable topspin shot down the line would travel 0.96 seconds, which does not afford the returning player with enough time to recover to the optimal spot. Now consider the situation in the lower right corner. Since the return goes cross-court, the returner is not required to recover to the other half of the baseline, so he has less distance to cover. Again, the low-angle chip's flight time would have been more than enough to recover to the optimal spot. Even the topspin return would have afforded the returning player with enough time to make it to an adequate position on court. He cannot quite reach the optimal position comfortably, but he is not far away. However, notice that the returner is pulled out wide for this serve. If, in this situation, he were to play a return down the line instead of cross-court, the returner would have more ground to cover to the optimal spot. At the same time, the reduced flight time of the return down the line affords the returner with less time to make up that distance. In this situation, where the returner is pulled somewhat out wide and attempts a return down the line, only the high arcing chip buys him enough time to get into the optimal position at the time of bounce. Up until this point, we have tackled the chip return entirely descriptively. We know, roughly, what an average challenger level player does with respect to the chip return. What we are lacking is an answer to the question, what should he do? Given the 12% win rate deficit of the chip return on aggregate, should the return be chipped by choice at all? And if yes, where and how? To this end, we estimate a model on our data that calculates the returner's win probability by taking into account a variety of factors, such as return placement, launch angle, speed, spin, and on-court positioning of the returner and the server. We can then use this model to find the most promising return in any specific situation. Take, for example, this very situation here. Alexandre Muller is pulled slightly out wide by Luca van Asscher's serve from the deuce side. The orange area shows our model's target zone for the returning player on a topspin shot. A typical topspin shot that lands within the target zone improves the returner's chances of winning the point to above 50%. In calculating this target zone, the model not only takes into account the probability of winning the point if a ball lands anywhere in the court, but also the deviation of the landing location from the intended target. Therefore, areas too close to the base and sidelines are excluded as targets. In 3 words, the target zone basically says, aim here, and if you make it, you'll win the point more often than you lose it. Our model believes that it is best to hit the topspin return cross court when a right-handed server serves out wide from the deuce side of the court. All the examples following will be depicted true to a right-handed server. In case of a left-handed server, simply flip the entire situation and the target zone across the middle. The forehand side is then on the screen's right, and the exact same cross-court return would be optimal, according to our model, on an ad serve out wide. As for the low chip, the model likes the cross-court return again, slightly preferring width over depth compared to the topspin target zone. For a high arcing chip, shown here in light blue, the target zone is considerably smaller than either the topspin return or the low chip. Let's take a closer look at the target zones. The flags indicate the highest return or win probability spot within the target zone. For example, if a typical topspin return lands exactly at the base of the orange flag, the point will be won by the returner 57% of the time on aggregate. Though the target zones for the topspin and the low chip return are almost of equal size, the low chip return has a higher win probability at the peak. The high chip, having the smallest target zone and the lowest peak probability, is discouraged by our model in this situation. Consider now a serve down the middle from the server's forehand side. For the topspin return, the model indicates a very generous target zone, ranging from the server's feet to his backhand side. On the other hand, the model still recommends to play the low chip cross court to the forehand. Again, the high chip has the smallest target zone, requiring depth and width on the server's forehand side. The topspin return is the safe bet, having not only the largest target zone, but also a solid peak win probability of 60%. The best possible outcome is a perfect low chip, deep into the forehand side, but win probabilities fall off fast around the peak, making for a smaller target zone. The high chip appears to be the inferior choice on aggregate. Up next, a serve down the middle from the server's backhand side. Similarly to the forehand side serve down the middle, the backhand side serve down the middle should be returned anywhere from down the line to the server's feet. However, presumably because now the return lands on the server's forehand side, the model requires greater depth to bring the returner's chances to above 50%. The recipe for a good low chip is bizarrely consistent. Target the server's forehand with good width. No change also in the high chip strategy. The target zone remains woefully small, deep on the forehand side. A closer look at the target zones reveals a similar picture. As in the other cases, the low chip return is potentially high risk, high reward, having a small target zone but high peak compared to the topspin return. Finally, we have a serve out wide from the server's backhand half of the court. In this situation, the model recommends playing the topspin return strictly cross-court. Recall from the earlier discussion that the returner is afforded very little time to reposition on the topspin return. On wide serves, the returning player is already off the court. The model therefore sees it as imperative to send the ball cross-court to reduce the distance the returning player needs to cover to get back in position. The low chip target zone is on the forehand side again, though decidedly smaller in this case. In this isolated case, the high chip target zone is actually larger than the low chip zone. Though the returner would play himself out of position going down the line, the model takes into account that the high chip affords the returner with plenty of time to recover to almost anywhere along the baseline. As we saw earlier, this is especially useful on the down-the-line return from out wide. Nevertheless, the topspin return cross-court is unambiguously the best option here, pairing the largest zone with the highest peak win probability. So in all cases except the backhand side serve out wide, The low chip is a high-risk, high-reward alternative to the topspin return. The remaining mystery is why the model wants the chip to be played to the forehand in all situations. Typically, the serving player can redirect the ball and inject pace more easily, so why chip to the forehand? To explain this result, we first divide the server side of the court into 4 parts, from A on the forehand side to D on the backhand side. Depending on the area in which the return lands, we look at the returner's success rate, depicted on the y-axis. While the returner's success rate on a topspin ball generally increases as the ball is hit farther to the backhand, the picture for the chip return is not so linear. Returning into B, that is slightly to the forehand side, promises the highest success rate, whereas returning into C, that is slightly to the backhand side, is the returner's worst choice on aggregate. One reason for this could be that chip returns, by virtue of their longer time in flight, are easier to run around, allowing the server to hit a forehand on a ball to the backhand. Let's verify this by looking at the rate at which a ball is hit with the forehand by the server on the third shot, depending on the area that the return is hit in. Unsurprisingly, virtually all returns are replied to with the forehand if they land in the forehand half of the server's court. However, more than 80% of chip returns into C are run around and hit with the forehand. Even if a chip lands in D, more than half of the time the server will have time to run around the chip and reply with the forehand. The data also shows that running around returns to the backhand pays off for the server. If a return to the backhand side can be run around, the server's win percentage goes up from 53 to 57% in area C and from 50 to 59% in area D. This might be the key in understanding why the chip return should be played to the forehand right away. If it goes to the forehand, the server may be tempted to attack the return with a serve +1 down the line, a risky shot that the server has to generate most of the speed and all of the topspin on. However, as we have shown earlier, attacking a chip on a serve +1 is premature on aggregate. A server is typically much better off setting up a serve +2 combination against the chip return. If the chip can be run around, the server has 2 ways to do so. He can still go down the line with the forehand inside in, forcing but risky. Additionally, there is the forehand inside out, attacking the returner's backhand cross court. At comparatively low risk, it lends itself well as a setup shot in a serve +2 combination. The 16 cases we are showing here are chosen to be representative with respect to where the server places them when he can run around the backhand. Only 3 times out of 16, that is less than 20% of the time, does he go for the passive forehand down the middle. Around half of the time he goes for the forehand inside out, and about a third of the time he goes for the forehand inside in. Now let's see what happens, placement-wise, if the return to the backhand is not run around. A few representative backhands go down the line. Some others go cross-court. But for the most part, our representative backhands go rather passively back toward the middle of the court. Putting it all together, we have confirmed that the model has good reason to avoid the backhand side chip return. It is unwilling to give the server the possibility of running around the backhand and hitting an inside-out or inside-in forehand. So, to summarize, for a specific set of players in a sample of 20 tournament matches played, the chip return is a viable strategy as long as it is hit low and wide to the forehand of the server, with maybe an exception on a serve out wide from the server's backhand side. The topspin return is always a solid choice. The way to go here is to hit cross court if pulled out wide, and to the feet or away from the server if the serve is down the middle. Note that these are aggregate results. They relate to the average challenger level player. Strictly speaking, however, the average challenger level player does not exist. This analysis would be more actionable if it was tailor-made for one specific player, but for this we'd need much more data. However, in principle, the methods and the models would be the same and would allow us to state with some confidence how to return a ball against that specific player on serve.